Hi, in today's video we're going to be talking about reactions on aromatic rings. So the previous class we saw that aromatic rings are not very reactive and they can react, we just need to use really strong electrophiles or strong nucleophiles. But today we're going to be talking about electrophilic aromatic substitution. So electrophilic aromatic substitution, as the name might tell you, is when you react a strong electrophile with an aromatic ring, in this case benzene, and it gives you now a substituted benzene ring. So let's look at the mechanism of how this happens. Well, first the benzene ring, one of the double bonds of the benzene ring, reacts with the electrophile. This gives you now a broken aromatic ring where you still have some stabilization of these pi systems into this positive charge, but you've broken aromaticity. So that's a very much an uphill or an energetically costly step. I've highlighted some of the hydrogen atoms that are on the molecule already for us to keep track of them in the reaction mechanism. And again, there is already stabilization or some degree of stabilization through this pi system here. So now we have solvent come in and abstract the proton adjacent to the hydrogen, adjacent to the electrophile, or on the same carbon as the electrophile. And this gives us back an aromatic ring, so we regain aromaticity, and ultimately we regain that stabilization that we once had. So that's, again, a pretty powerful driving force. So there are some things we have to think about in the context of these reactions. The electrophile, must be quite reactive, as I've said several times. And also the conditions are often quite acidic. So that will be important later on when you're looking at the different electrophiles. So let's look at, before looking at the electrophiles, let's look at how what's on the aromatic ring already is going to direct where the electrophiles are going to go. So there are different types of groups. They can be either electron donating, a lot of times we'll write EDG, electron donating groups, or electron withdrawing groups, EWG. And these can often react as both, using both resonance and using electronics in terms of thinking about these. Electron donating groups, often you invoke resonance arguments for strong electron donating groups. So let's look at where an electron donating group is going to direct an electrophile. And, but before doing that, let's talk about how we name these different positions. So if this highlighted hydrogen atom at the top of this benzene ring is position 1, the two positions directly adjacent to it are called ortho, or O, often abbreviated O. The positions next to that are meta, or M, and then the position exactly opposite of it on the ring is called the para position. So ortho, meta, para. There are 2 ortho positions, 2 meta positions, and 1 para position. And as you may have noticed, I've highlighted that electron donating groups are often ortho para directors, and we'll see why. So if you draw a resonance structure of an electron donating group donating electron density into the aromatic ring, the first resonance structure you have puts a negative charge on ortho. Keep in mind that electrophiles are positively charged, so the negatively charged carbon is going to interact with the positively charged electrophile. Similarly, you can also draw a resonance structure that puts the negative charge at the para position. If you were to draw another resonance structure, you could draw it on the other ortho position. I'll ask you to do that on your own for practice. If now you look at the electron withdrawing groups, you can notice electron withdrawing groups in the same way that the donating groups are putting electron density into the ring, which is going to make them more reactive. Electron withdrawing groups are going to be pulling electron density away from the ring, and so they're going to be making them less reactive toward the electrophile. So again, there's less electron density available to the benzene ring to do those reactions we saw on the previous slide, and so therefore they're not going to be as reactive with the electrophile. They can still react, but we typically need to heat them a little bit more or let them go a little bit longer or force them in some way. So again, electron withdrawing groups, you can think about arrow pushing mechanisms as well. where now the electrons are getting pulled out of the aromatic ring, and so you end up with a carbocation. So, a carbocation interacting with an E+, that's not very favorable. So they're certainly not going to go to the ortho position. They're also not going to go to the para position. And so the way to think about electron withdrawing groups is that ortho and para positions are especially bad in terms of their reactivity. The meta positions, you notice that there are no positive charges on the meta position, so they're just kind of meh. They are, again, it's electron withdrawing group, so it's not going to be a favorable reaction, or it's not an easy reaction, but that is where the electron withdrawing groups will typically direct an electrophile on an aromatic ring. Let's now look at some examples of electron donating and electron withdrawing groups. So for electron donating groups, we often have groups like a hydroxyl group, an OH, an amine, NH2, and an amine where there are carbon atoms attached to it, so NR2. You could also have a methyl ether, or even just an alkyl group. Electron withdrawing groups, some examples of electron withdrawing groups, a nitro group is especially electron withdrawing. A nitrile group, we'll see that, or you saw that recently as well. Nitrile is also quite withdrawing. Carbonyls, directly bound to an aromatic ring, are electron withdrawing, as are halogens like chlorine and bromine. I want to point out here we have an amine, NH2, and an ammonium, NH3+. So an amine is able to use its electrons to donate electron density into the aromatic ring. For the ammonium, there are no extra electrons on that nitrogen atom, and so it's now being purely inductively electron withdrawing. That can be a challenge when you're trying to plan out reactions because, as I mentioned before, the reactions are often done under acidic conditions that would protonate this amine, turning it into an ammonium. That can really mess up your plans when you're trying to decide how to add groups onto aromatic rings. I want to highlight here that the halogens are unique in how they are electron withdrawing groups. All the other electron withdrawing groups, or all of these electron withdrawing groups, will be, these meta directors, but chlorine and bromine are ortho-para directors. And that's because if you look at this resonance structure, for example, the one with the para, you could also practice for yourself of the one at the ortho position. This puts a carbocation directly adjacent to the halogen. The halogen does have electrons on it that are able to donate a little bit. We typically don't draw these as resonance structures, but you can think about it kind of like hyperconjugation. So it's donating a little bit of electron density into this carbocation. That's actually the hyperconjugation argument is why alkyl groups are ortho-para directors as well. I'll also highlight, though, that even though it's donating a little bit of electron density, it is still inductively pulling electron density out of the ring. So again, that is not favorable, and that's why chlorine and bromine are indeed electron withdrawing groups. So let's look at some electrophiles and how we're going to generate these electrophiles. So here are the electrophiles. I'll put the electrophiles on the left, and the reagents to give us those electrophiles on the right. So the first is this acyl cation. This is a very reactive intermediate. You've not seen these drawn before, but these are generated again when you treat an acid chloride. We've seen acid chlorides before. They're very reactive species with aluminum trichloride. So aluminum trichloride effectively pulls the chlorine atom away from or off of this carbonyl carbon, and it makes it even more electrophilic. A cationic bromine atom can be added as an electrophile when you treat bromine, Br2, with iron tribromide. Similarly, chlorine, Cl2, with iron trichloride will give you the Cl+. So again, a very similar mechanism to the one above is that the iron effectively rips one of the bromine atoms away from the other one. If we're trying to simply add an R+, so this could be like a methyl, ethyl, propyl, things like this, you can have your alkyl halide, and again you use aluminum trichloride, and similarly the aluminum kind of pulls the chlorine atom away from the carbon so that you're generating this really potent electrophile. Finally, if you're trying to add a nitro group, an NO2 group to your aromatic ring, you treat nitric acid with sulfuric acid. So again, that's a very highly acidic situation, and this is going to nitrate your aromatic ring. Let's look at an example of how this might look in a synthesis. So if you had a benzene ring and you're trying to have this nitrobenzene, the conditions that you would use are nitric acid and sulfuric acid, so you're doing a nitration reaction. And now that you have a group on this ring, an electron withdrawing group, you have to realize that this electron withdrawing group is going to be a meta-director. So now for these next conditions, aluminum trichloride with ethyl chloride, so you're going to be adding an ethyl group, again, 2-carbon group onto the aromatic ring, you're going to expect that it goes in the meta position. So let's now look at if you were to switch these two reaction conditions. So you use aluminum trichloride first, and then add the sulfuric acid with nitric acid. Is that going to give us the same product? You've probably noticed that I like setting up situations where they're not. So no, it's not going to give us that compound, and let's see why. Well, the first reaction, aluminum trichloride with ethyl chloride, is going to give you this ethyl group, but ethyl groups are electron donating groups, so they are ortho-para-directors. And if you have a group on an aromatic ring, typically the ortho position is blocked due to steric interactions, so the major product is going to be the para-directed nitro-aromatic. As one last thing to think about for this, before we wrap today's video up, well, what if there was a bromine atom instead of a nitro here? So I'd like you to work through this process of, instead of getting to nitrobenzene, I want you to make bromobenzene. And then what would bromobenzene do with aluminum trichloride and ethyl chloride? And then if these conditions were swapped, what would the product be? So think about that, ask questions. I look forward to seeing you in class. Thanks.